but recursion can only be implemented in those languages which supports recursion. Now, what we are doing is that we can also write a non-recursive algorithm for a traversal. In order to perform a non-recursive algorithm, we have to maintain a stack ourselves. Now, today I'll show you one of the traversals which can be done using a non-recursive algorithm, and you can develop other software, other traversals similarly. Now, let us try to make a tree. Suppose I want to make a tree like this. Suppose I have a tree. Now I'm taking this from the one of the book of the. Now this is the overall tree where A is the root, and you want to find the non-recursive algorithm for this tree. Now, if I am performing, let us perform in order traversal. What are the nodes which will come in order traversal? You will get left, root, and right. Now, obviously, if I am going to do it by just by looking, I will be getting, say, G, I'll get this. Okay, G, D, H, K, B, A, E, C, F. Because you have to go to the leftmost, G, then root, D, then H. Since there is no left of H, therefore H, then K, then keep on going backwards. I will reach to B, process B, there is no right of B, therefore you go back to A. And if you are processing the right subtree, it will be ECF. Now, this is the traversal. Now, let us write a non Now, it's quite simple. If you are going to perform a non-recursive algorithm, it's quite simple. You have to maintain a stack. If what I am going to do, I'll maintain a stack like this. And here, initially what I'm going to do, I'll push a null value. I'll push a 5. That means I'll put a null value. Null is nothing but a 5. And then I will try to use one pointer which might be called as, say, if I call it, say, PTR. Now this pointer is the one which will point to the root, and this will be coming down as and when you want to. Since we are doing an in-order traversal, what you have to do is that you have to try to find the, if you are going to do an in-order traversal, you have to come to the leftmost node, isn't it? Now tell me, how will I proceed? Okay, how will I proceed? Now initially stack is 5. Now what I will do is that I will set PTR is equal to, therefore what I will say, set PTR is equal to root. That is A. I will set PTR is equal to root F. That is PTR is set to A. Then I will keep on moving down and I will come to that node which does not have a left child. That means I will start from PTR and follow the nodes from A down to the node, that node which doesn't have a left child. Now in that case, you will reach to G. But before going that, you push all the nodes in between. Therefore, what I am going to do, I will say A is having a left child. Therefore, I will push A. Then I will come to B. B is also having a left child. I will push B. Then I will reach to D. D is also having a left child. I will push D. Now these are the PTR numbers. Then I will reach to G. Okay. I will reach to G. I will have this. I will push G. Correct? Then I find that there is no left child of G. Then what I do is that I pop G. When I pop G, G will come here. And here you will get. Then you will reach to G. Since G is not having a right child, you will move to D. Therefore, you will move to D. Now here, what will happen? Now you will go back to D. That means now D is at the top of the stack. Then if D is having a right child and you already processed D, therefore remove D over here. You are going to remove D over here and process D over here. Then you have to follow the right child and now PTR will come here. If H is not having the right child, therefore you have to process that. If H is not having right child, you have to process that one. Therefore, you might find you might push H over here and then check whether it has a left child or not. If it doesn't have a left child, you just remove this from here and put it over. Then similarly, you go to the right, PTR will now come here. And here you push K. And then try to find if K is having a left child, K is not having a left child. Therefore, you pop K out and you come over here. Then it doesn't have the right child, therefore, you keep on going backwards. And backwards means you from the stack itself, then you take the B out and push B over there. Then you find that B doesn't have a right child, therefore you pop A. Pop A and A will come. And then you follow the right child, you will come to C. Therefore, in that case, what will happen? You will come to C. Now you will find that C is here. You see, push C. Now PTR will come here. Then you find that it also has a left child. Therefore, you push E. Then here you find that E doesn't have a left child. Therefore, you pop E out. And then you are going to pop C. And then you are going to F. Therefore, you will now go to F and push F. Then you find that F doesn't have a left child, pop F. Then after that, you find that F is not having a right child also. Therefore, you pop. Once you pop, you get a phi. Once you pop here, once you pop this, you will get the null. And this means that there are no more elements to process. And therefore, you got the traversals. That means once you are going to perform a traversal, you can maintain the stack and you can keep on popping the element until the stack is empty. Now, when stack encounters a null value, it means that there is uh, no further element. Now, what I will do is that if I am going to write the algorithm, I will just do that. You proceed down to the by pushing all the nodes in between, and therefore you just show the status of a stack. Now here, if I am going to do that, the stack will be something like this. It will be 5, then it will be A, B, D, and C. These are all nodes. And that's all you keep on doing, and just you get the traversal. And whatever I said, you just keep on doing until you find that the stack is empty. Correct? Now, if you are performing a pre-order traversal, the only difference what you are going to do is that you are not pushing the root. Instead, what you are going to do, you process the root and push the right child, isn't it? That means if I am doing, maybe I am doing a pre-order traversal, what I am doing is that once I process A and push the right child, that is the C. Then I go to B, process B and push the right child. Then I go to D, process D and push the right child. Just just modify the algorithm with one word, it's become a pre-order. That means here I am pushing the left child. I am pushing down the leftmost node by pushing all nodes. Instead of all nodes, you have to write only the right child. And that's all. The algorithm is very simple. You can very well write the non-recursive algorithm for this. Okay. Now for all, it is almost same. Is it okay? Is it clear? That means you can always write a non-recursive algorithm for a tree traversal. But of course, you require an additional data structure, which is nothing but a stack. Okay. Now, the next question is, can we avoid a stack so that I might may be able to do the whole concept without performing a I can do the whole non-recursive algorithm without maintaining a stack. Now that is little question. That is, in this case, is obviously not possible, but we can do it in some other way. If it, we'll try to do one of the very important concept which we'll do, which is there, which is called I'll use the important concept called as a threading. A threading. Threading is a concept where you are going to, to join the nodes using a thread instead of a link. Now let us try to make a tree, something like this. Now I am taking from the book so that you will be able to do it. Okay. Now I am going to make the threads for this. If I write like this. Correct? Now this is the tree. We are using a linked list. Now you find that how many links are there? All the yellow lines. Therefore, it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Therefore, you find that there are 10 links. How many are null values? Obviously, you check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Therefore, there are 10 null. Correct? Now, this equally just a coincidence. It doesn't mean that every time links and nulls will be same. It can be very different. It can be more number of links, less number of nulls, or it can be anything. If it doesn't mean that it is always the same. But here, what I find that a considerable amount of space is being wasted just because of having a null pointers. Now the question arises, can we utilize this null with some meaningful information? Can we do that? Yes, we can do that. For that, we have to perform the threading. Now threading is going to work on those null values which will contain the threads instead of a link. The difference between thread and link is that link points to parent to child, whereas thread points from child to parent. The parent may not be the immediate parent, will be an ancestor for that. Ancestor means, for example, for L, the parent is J, but L might point to H also, or it can be anyone, depending on the threading. Therefore, a thread are basically backlinks. Backlinks from the child to the ancestor. Maybe it is going to point to the ancestor. Now, I'll show you how to perform a thread. Now, before we do this, what we are going to do, we are going to take a header node for this. Now, what I'm going to do, you just try to understand the concept. I take one header node. Now, this node is called the header node, which contains a pointer like this, and therefore, in this one, this will contain a null. Okay, there will be no data for this, and I will maintain a simple. I'll maintain a simple head which is pointing to this. Now this node is called a header node. Now this is called a header node. This is called the header node. And this head is just a pointer which points to the header node. And the header node left pointer points to A. And this is the actual header node what I am talking about. Now, what I am going to do is that I am performing the threading for this. Now this is all. Now what we can do when you are going to perform a threading, you have to first of all tell the threading for that. Now let us try to write in order threading for this. Now what I'm going to do, let me write now tell me what is the in order
Sir, sir,
yeah,
excuse me. So why you can't tell the A node is as a header node?
why? Because
Yeah, we why? Yeah.
that's the root. I'm going to make a header node which will pointing to the A. Now we'll come to the thing that why I need that. I can directly point ahead to the A also, but this will not this can work because you are having a tree like this. It could have been a tree which there could be two trees which might be may not be connected to a single node. Therefore, I'll come to the conclusion because but this I'll come to this. Let me first of all cover the in-order threading. Now tell me what is the in-order threading when in-order traversal for this tree? बताओ. Just try to get this. In order means left root right. सबसे पहला कौन सा होगा?
D.
D. Then
D. B. E. F. A.
ठीक है. B B E नहीं E नहीं होगा सॉरी. अब तुम्हारा वो है ना F E होगा. Because left hand root. Therefore D B. When you come to E, you cannot process E because they left of E also. Therefore F E and A. Then you come to this branch. In this branch you have the leftmost. That means G. Then you will come to C. Then you come to this tree, H, J, L, K. But you have to first process L, then J, then H, and then B. Just verify it's correct. D, B, F, E, correct. A, then G, C, then L, J, H, K. Fine. Okay. Now, what you have to do is that all those links which are there, I have to use the back pointer with this. Okay. Now, where are the nulls? You have a null here, you have a null here, you have a null here. All these are nulls. This is all. Now, what I will do, I will perform a one-way threading. A one-way threading is that where you are going to only perform a threading with only one of the links. Now you just check B, both the links are occupied. Therefore, you cannot put a thread to this. With D, what is the successor of D? What is successor of D? You just check. You check here. It is B. Therefore, what I can do, I can make a back link from D to B. Then, what is the successor for F? Is E. Then, what is the successor for G? G successor is what? C. Therefore, I will make line. Then what is successor for F? It is E. Therefore, if kahin ho gaya. Then what is successor for J? Is H. What is successor for K? Nothing. What is successor for L? Is J. Okay, that means I am just targeting the right links. I am just targeting the right links. Now this is the where if I am performing a one-way threading, I am just trying to target the right part of things. Now in this case, you find that there is one more right link is left, is right link of E. What is successor for E? Is A. Therefore, I will have a right coordinate. Now
Excuse me,
all
sir.
the,
Sir,
yeah,
1 minute. Sir, here, sir, we have the stored the sir. We have make a threading with for H with J. That means the sir J null address is has been filled by some address. Now, sir, we are linking L to J. Then how it will store? There is no space. There is no. I mean,
in right is blank. Right of L is blank only. No, it contains a null value.
yeah, but sir, it is pointing to H by the link by the threading. Then, sir, after that threading, how can we, sir, make a thread from L to J?
Hey, repeat again the question.
Wait, 1 second.
Hmm. Hmm.
Sir, here J is we have make a threading from J to H
Correct.
by the from the right side,
Uh,
and again, sir, we are making thread from L to J.
hmm.
Then how, sir, it will work? Because we have already filled the null pointer
It's not like
of
that.
J.
See, for L, this is null. For J, it is something like this. And this is null. Then for H, it is something like this. This is the scenario. No, sorry, not this one. And this is H is also pointing to somewhere like this. Okay. This is the thing. No. Now, what are backend? This is backend. Now this is backend. This is backend. I am pointing a link from here to here. That means I am putting the address of J in the right of L. No, this is blank only. Then I am putting the address of H here. I'm putting the address of H over here. That means I am putting the address of H in the right of J. No, that's backend. You cannot put a address where you already have a link. I cannot put it over here. So I cannot put it over here. I cannot put. I cannot put here. I cannot put here. I cannot put at this place, this place, this place, because already it's occupied by a link. But where are the nulls? I can do that. I can even do here. I can even I can do here also. I can do here also. At this place also. At this place also. But I am not targeting the left link because for a successor, I only check the right links. Therefore, I am only targeting the right links. And you see in this figure, all right links are used except the last one. The last one is what? Is K. Therefore, right link of K cannot be used because there is no successor for K. Is it clear, Shashi? I am putting a back link from the child to the parent. But I told you parent doesn't mean the immediate parent. For example, if you see over here, the parent of E is not A. The parent of E is B. But A is a successor for E. That means it is a grandparent. You can say in that sense it's a grandparent. Therefore, it might point to the immediate parent or might point to a grandparent or might go, even point even further up the line. Now, in this case, all your right links are occupied except for the last one. That means this one, the K one. And then what you have to do is that you have to fill this with a null value. That means there will be only one null value in the entire tree. In the right links, either it will be occupied by a link or it will be occupied by a thread. And this is the one way. Now this is the one way. This is the one way. This is the one way not of threading. Correct? Any problems? That means I am only using the right links, and only one of the right link will be containing a null value. Okay. Now,
Okay, sir.
if I am going to perform the traversal, now let us try to find this how I am going. Now, is it clear to you? Because now I will be performing a traversal. You start from A. You start from a pointer from at A. Then what I am going to do, I start with a pointer at this place, PTR. Then I go to the leftmost of A. I will point from there to this place. Now I find that B also has a left child. I will come to here. Then I find that here D doesn't have a left child. If D is not having a left child, you are going to process D. Then what I am going to do is that I am going to process D. Then I have to go back. I'll follow the thread from D to B. Once I follow this thread, I can go from D to B because D, right of D contains the address of B, and therefore I can go to B. Once I go to B, I process B. Then from B, I find that it contains a link. Therefore, I will come to E. I'll come to E. From here, I find again left of E contains a link. Therefore, I will come to F. From F, I find that the left of F contains a null. Obviously, this will contain a null. That means I will process F. Then, what I will do, I will follow the back pointer because F doesn't have a right child. Therefore, I will follow the back pointer, this one, and will come to E. Then I find E doesn't have a right child. Therefore, I will follow this one, and here I will process E, and then I will come to A. When I come to A, I have processed all the left of A. Therefore, I will process A, and then similarly, I will follow the right link of A and will come to C. But I cannot process C because C is having the left child. Therefore, I'll keep on finding the leftmost child and I will come to G. Now, when I come to G, I find that the right of G is now null, left of G is null. Therefore, I have to process G and I process G. Then I will come to the right of G. I find that there is a thread. I go back from here to C. And then I process C. Now, meaning is that once I go with a thread to that node, I process that node because I know that I will process all the back pointer, all the left pointers of that node. Once I follow from G to C via thread, I process C. And then I follow the right of C and I will come to H. From H, I will come to J. From J, I will come to K. Sorry, from J to L. And from L, I find that this contains a null. If it contains a null, I process L. Then I want to go to the right of L, but there is no right of L. It contains a back link. Therefore, with this link, I come to J. Once I come to J with a link, with a thread, I process J. Then I try to go to the right of J. There is no right of J. Therefore, I follow this thread and come to H, and I process H. Once I process the H, I want to find the right of H. This is already, therefore, I am following. This will come to PTR. Then I want to find the want to go to left of K, but left of K also contains a null. Therefore, I process K. Then I want to find the right of K. Now here right of K contains null. It means your traversal is over, because that is the thing you have to find. I told you that only one of the right of the link is right of the node contains a null, and if it contains a null, it means that that is the last node, and therefore you see there are there is only one of the thing which contains the yellow nulls. Now this is the one which I therefore I am trying to write it very clearly. This is a yellow one. There is only one of them. All the other ones are basically red ones, which are basically left links. Now here this is also red, left. Now how many reds are there? 1, 2, 3, 4, 5, and they, 5. 5 red links are there. Red links are basically left links. Yellow ones are the one which are right links. There is only one yellow, and other all are either containing links or containing threads. Now in that case, it means that without using a stack, I can perform a thread. I can perform a traversal, and you are saving the entire space of a maintenance of a stack. Is it clear to all of you? Now, one thing is important. How will you differentiate a thread with a link? Thread, for that, what I will do, thread will contain positive integers. Sorry. And threads will contain negative integers. Links will contain all positive integers, whereas the threads will contain in negative values. Now, once I get a negative value, I will be knowing that this is a thread. But while going from the back, that is thread, I will consider it as a positive value only, because addresses cannot be negative. That is just to make you aware that if a negative value is encountered, it means the thread. But once I am going to process it, I'll process it as a positive value only. Let us take an example. Suppose this contains the value. Suppose this contains the value. Suppose this address is 2500. Now here you will find that I have stored minus 2500. Okay. Now once I follow from F to E, I read the right part. It contains minus 2500. I get the modulus part of that, it is 2500, and I can go from F to E via the thread. I am doing this because threads are basically back pointers. I cannot put if I put a negative address into a thing, it will search a negative address of the RAM, but obviously there is no negative address in the RAM. Therefore, you have to intelligently just convert this minus 25 to 2500 by just using a mod function. A simple modulus will do. And this is how you are going to do. Is it clear? Now this is how you are going to do. Now this is a one-way threading. In a two-way threading, what you are going to do, all those red links will be replaced by the predecessor for those nodes. That means I am going to replace all of them with the predecessors. Okay. Now in that case, all these red ones will be replaced by the predecessors. Now tell me, इसमें कौन सा ऐसा होगा जिसका के how many of them will contain null? If I am going to go for two-way threading, कितने ऐसे null होंगे? How many null pointers will be there? Now what? It will be only contain two null pointers. One, the predecessor for D and the successor for K. K के बाद में कोई नहीं है और D के पहले कोई नहीं है. Therefore, there will be two nulls. In that case, that is the whole thing you will do like this. अब हम करते क्या है, तुमको एक बार दिखाए थे करके टू वे स्टडी. I draw the simplicity like this. ठीक है, this is the same one which it's the same here, the same A B C D E G H F J K L. See. Now I am going to make the threads. Now just check how many threads were there. See how many threads were there? 1, 2, 3, 4, 5, 6. Only 6 threads were there. This 1, 2, this green one, this 3, the 4, 5, 6 threads were there. Now you see over here how many threads are there? There are 6 threads. Now try to find the left pointers. Now you just come to a traversal. Now let me write the traversal. So there's 2K. Some mistake somewhere. Now just check it. D B F E, fine. A, then G C, correct. Then L J H. Then G C, then L J H. Fine. Now this is the okay. Now let us try to find the predecessor. What is the predecessor for F? Is B. Therefore, I use a back pointer and I will use it like this. Now, what is the predecessor for? Say you see for E. E is F. but you can't do because now you check where are the left nodes free. It's free for at G. What is the predecessor for G? Is A. Now for H you can't do because H both are filled. For J left you can't do because it's already filled. Now what remains is K. What is the predecessor for K? Is H. Now for L, what is the predecessor for L? Is C. Therefore, what you will do? Now here is that you are going to put it back. Fine. You have filled all the links except two, left of D and the right of K, which is not there. Now for that, what I will do, I will have that I have maintained a header node. Now what I will be doing, I'll point this and I'll point this. That's all. And you know that this always points to this one. And the right of the header node is not having anything. Then what I'll do is that I'll put the address of self node. Therefore, what I will do, I will using a because instead of I'll put this same as this. That means I'll put the itself address of itself. Now you find here that all the left, all the rights are now occupied. All the left ones are pointing to the predecessors. Now in this case, the left ones, the left points to predecessors and the right points to successor. All the left pointers point to predecessors. Obviously, this holds for the threads, all left threads. Now, what I will write? I will write for threads. For threads, all left is pointing to the predecessors and all right are pointing to the successors. And this is the two-way threading. This is the two-way threading. Obviously, it's in order. It's in order threading with a header node. Correct? That means the advantage of having a thread is that you eliminate the maintenance of the stack. And when I am having a stack, you are not going to use there is no need to use a stack for this. I can traverse using a thread without ever using an extra this space. I can perform a traversal. Though a stack is also convenient, but that requires the push and the pop operations and plus maintenance of the stack. This is the easier one because with the same data structures, you can perform this. Now, also I can even maintain it using an array also. That means I can maintain an array which contains three parts. One, the data part, second, the left, and the third is the right. Therefore, I can also do like this, which is another very good thing. I'll tell you tomorrow. I can maintain an array like this, which contains the data, the left, and the right. Now the data is nothing but ABCD, whatever you put. The data will be here, say A, B, and C, something like this. The left ones will be the position of A. Now here if I am going to put like this 1, 2, 3, 4. Now if I want to find that B is the left of A, therefore in the B of I will in the B part, in the left part of A, I will put the position of B. Now what I will do, I will put this as 2. Now what is the right of A is C. Now I will put here 3. Now try to see it how intelligently it is being done. I put the data, all of the data, A, B, C, D, and whatever is there, and then I put the left of A is B, the index of B is 2, I put 2. Then the index, the right of A is C, the index of this is 3, therefore I put 3. Now for the B, I find the index of D. Now here, if D is over here, and I find that the left of B is D, I put over here as 4. Where there is null, I'll put a simple dash. I'll put a simple. For example, if I put for E, E of left will contain some index, and the right of E will contain a dash. But if you maintain you are going to maintain a threads, you put some value of say -6. -6 means that is a thread from that position to that position. And therefore, this is one of the ways to maintain a tree as an array also. You can also maintain a tree as an array. Therefore, I just explain it tomorrow, this one in details. Therefore, I don't mean to say that you always do it as an array, but there is a way out. If I know that there are only n number of nodes and n is not going to increase a lot, say dynamically, I can use an array also. For example, I know that only 10 nodes. I can maintain an array for that instead of using this linked representation. But if it is going to exponentially or if it is going to dynamically increase, I should not do that, because that is a difficult task, because you have to every time you have to modify the size of the array. Now, any questions?
Sir, what will be the syllabus of our sessional, sir?
I'll write down. It will be only that stack